Hi, welcome back. So we are in Chapter 3, Descriptive Analysis, in the section of Dispersion to discuss the variance and standard deviation. Now, capturing one, it's easy to capture the other. The actual meaning of standard deviation is just the square root of the variance. So let's go ahead and have visual presentation on the actual meaning of variance. It is possible to capture the variance for both continuous or a discrete, but basically from my personal experience, I don't really study the variance when it happens that my scalar to be discrete, because I look for the table of distribution that give you much more intuitive information. But when it comes to my scalar to be a continuous value, variance is really a good tool that you can look at, of course, plus the standard deviation. If it happens to be this is your population, then the sample of variance usually come in the form of sigma squared. And just since you are taking the square root of this, then your standard deviation will be sigma. Okay, but if it happens that is just a sample s square, of course the standard deviation will be only s. What is variance actually? The story starts from the mean. Now we know what is mean. We learned how to capture the mean. Now if it is population, then it's a mu, Greek letter, or if it is a sample, it's just x bar. Now once you have the mean, the value of the mean, it tells you your expectation. I think we discussed this before. I expect that every value actually in this vector to be equal to my mean. But that's not what happens. I've got another value for S1, another value, maybe the same for X bar, it doesn't really matter. So in this case, the difference between the actual S1 value and what you expect is actually variation. So we take just the power of 2 to avoid this minus term. This value, it's called the variation. Now to capture the variance, the total variance for everything that you have in here, we take the same exact thing for each and every value I have in my vector. And after you do that, you take just the summation. You need to divide it by m minus 1. Of course, the m, it's equal to the total number of samples, right? If this is a sample, then n minus 1. But if this is your population, you don't need a term of minus 1. This is what variance is all about. And why we need to do that, because this total value, it gives you intuition about the total sum of error from your expectation if you are well. If we take the square root of this, we will get STD, or the standard deviation, the average value of this error. The actual formula mathematical formula of your variance, so you take your x of I, right? And you subtract it from the average. Just take the square root of that. And don't forget, after you finish all this summation, divided by total number of m minus 1, of course. Now, just in a quick example, let me show you. Capture my x bar from here. Expected value, that every value in this vector I expect to be 4. But the actual, it isn't. When you sum up this, now I know this is my sigma square if this is a population, or my s square if this is my sample. By taking just the square root of this, this is my actual standard deviation. And what does that mean? So every value I'm gonna take, it will be deviated by 2.5. But there's one problem that we discussed. If you would have an outlier, the mean is sensitive to the outlier. And as a result of that, of course, your variance and standard deviation, all this calculation will be wrong. So that's why you need to make sure and always take into your consideration, handle your outliers before you even capture the mean or the variance or any of these central tendency tools. And that's why the study of IQR, which we interquartile, for example, was one powerful tool that shows you your vector have an outlier. That's why the sequence of choosing the right tool once you start your analysis is quite important. Next things we want to do actually is to look at two variables and how to start the analysis on them. And this is called the study of bivariate descriptive. I will see you then.